Tutorial 6, Part 2, Stress Concentration and Intensity, and Design Considerations. After we have talked about the types of failures, in this part of this tutorial, I will mainly talk about how can we predict when and wonder what situations the material will fail. And first ideas I will going to introduce in this video is stress concentration. As we know that not everything on this world have a uniform cross section, and that implies is at different position of a object, it will have different values of stress. And you can see here in this picture, this bar is certainly non-uniform in terms of its cross-sectional area. And the loading condition is there is a normal stress on this surface here equals to 300 Pascal. It is compressive, and the position here is fixed. And you can see that the stress within this bar is different at different positions. You can see here the maximum stress is actually located at the neck of this non-uniform bar, and it is marked by red color. So therefore, we must first to find the maximum stress within an object under certain load conditions before we can try to predict when it will fail. Because if this maximum stress exceeds the critical value for that kind of material, definitely it will fall. And stress concentration, basically, it means the position where the stress is maximum, or there is a extrema of the stress values. So how do we note this stress concentration won't exceed the safety limit for that particular material? Actually, we have two methods. The first one is the finite element method, and the second one is the stress concentration factor. However, for the first one, it will not be taught in these courses. And if you want to know that, you can go to and take Mechan 4150, which is finite element method, which is, in my experience, it is a nice course. Basically, it is using a finite element approach to approximate a differential equation, which is governing the stress and the strain within that material using a computer to find the solution for that approximation of the differential equation. And as my description suggests that it is a advanced content, so therefore we are going to learn the second method only, which is the calculation of stress concentration factor based on engineering correlation data. So we will learn the second method in this course. The stress concentration factor for a bar containing elliptical crack can be calculated using formula here. Kt, which is the stress concentration factor, is equal to the maximum stress will be appeared in this bar over the applied stress the applied normal stress, sigma law, which is equal to 1 plus 2 times square root 8 over rho t. A is the half crack length, and rho t is the crack tip radius. And this equation can be applied to both the typical crack, external one here, and the internal one, which is here. And KT has no unit. And this is just for elliptical crack. And there is also other engineering correlation data on different simple features other than elliptical crack. Let's use an example to further illustrate this equation. What is a maximum stress within this bar? 1 for half crack length A equals to rho t. 2 for A equals to 100 rho t. And the loading condition is shown here in this picture. As by the definition, KT is equal to the sigma maximum over the sigma log. Sigma maximum is the maximum stress within this bar, and sigma log is the applied normal stress, is equal to 1 plus 2 square root A over rho t. For case 1, KT is equal to 1 plus 2 times 1 over 1, or times square root 1, which is 3, because A is equal to rho t. And therefore, the maximum stress within this bar is equal to KT times the applied stress, which is 3 times the applied stress. For case 2, KT is equal to 1 plus 2, as A is equal to 100 rho t. Therefore, A over rho t is equal to 100, and square root 100 is equal to 10, and KT is equal to 31. Therefore, the maximum stress within this bar will be 21 times the applied normal stress, which is a sigma log. Stress intensity factor. Stress intensity factor, K, is not equal to stress concentration factor. It has a unit of Pascal times square root m. And it is applicable for materials already having small cracks within the materials. In real-life applications, nearly all materials already contain some crack, which is not visible to naked eyes. Therefore, we must consider stress intensity factor in the design of objects using these materials. Stress intensity factor is defined as Y times sigma times square root pi A. A has the same definition with the A within stress concentration factor, which is the half crack length. Sigma is the applied stress, and Y is a factor called geometric calibration factor, which depends on the geometry of the object. And actually, there is 3 kinds of critical values using the definition of K, which is K1C, K2C, K3C, which is also known as fracture toughness. Or basically, it is just the critical value for failures in 3 failure modes: tensile mode, slide mode, and the tear mode. And however, tensile mode is the most common failure mode. So therefore, we often use K1C as the critical value for a typical material in the design problem, which using that kind of materials. In real life design, we have several design considerations. After I have introduced these factors to you, the first factor we need to consider is the safety factor, which is often a factor having a value larger than 1. And apart from the safety factor, there is 2 more considerations. The first one, the maximum stress within the object using that particular material must not exceed yield stress for that particular material over the designated safety factor. Another consideration is K value, the calculated K value under such working loading must not exceed K1C for that material. K1C is the fracture toughness, the first mole fracture toughness for that material over the safety factor. Let's consider a uniform bar with yield stress equal to 200 megapascal, cross-sectional area equal to 60 cm square. Rho T, which is the crack tip radius, is equal to 2 cm. Crack length is 20 cm. K1C for this material is 30 megapascal times square root m, and the y is equal to 1.1. With a designated safety factor of 1.2, calculate the maximum allowable axial forces allowed. Step 1. Calculate the maximum allowable applied stress by stress concentration factor Kt. Kt, by definition, is the maximum stress which will be appeared in this bar over the applied stress, which is equal to this equation as shown in previous slides. A is given, rho T is given, and we just plug in the number. Be careful, A, we need to convert the unit for the value of A and rho T. And Kt times the maximum allowable applied stress is equal to the yield stress over the safety factor, which is 1.2 for this question. And therefore, the maximum allowable applied force is given by this equation. As we know that the maximum allowable applied normal force over the cross-sectional area, which is also given, is equal to the maximum allowable applied stress. And we just use this equation, we can get the values. Just plug in numbers and we can get the values. And also be careful that A is in terms of cm square. So we must convert it into m square. Step 2, calculate the maximum allowable applied stress using stress intensity factor K. K1C is equal to 1.2 times y times the maximum allowable applied stress times square root pi a. 1.2, don't forget to include it, which is the safety factor for this question. And we just arrange the term and we plug in the values. And be careful about the units. And we get that the maximum allowable applied stress is 40.5 megapascal. When we have the stress, we can find the force, as we have already given the area. Therefore, we find that the maximum allowable force is equal to this value. As we get two distinct calculate maximum allowable forces, one is smaller and one is larger, we must always choose the smaller one as our final answer, as we are engineers and we must make sure that it is safe. We must use a smaller critical value. Another design example. Consider the following list of alloys. Take Y is equal to 1.1. For applied tensile stress of 700 megapascal, which of them can be chosen? And which of them is the best choice? The safety factor for this question is 1.2. And here is the list of the possible alloys. A, B, C, D. The first thing we can exclude is alloy B. It is because when we considering the safety factor, which is 1.2, times the applied stress, it has already exceeded the yield strength for alloy B. Therefore, we have already excluded one choices. Therefore, B cannot be chosen as alloy used in this design. Other alloy, A, C, D, their yield strengths first satisfy the requirement. However, when we consider the fracture toughness, which is K1C, for A, just find the value. 1.2 is the safety factor. Y is equal to 1.1. The applied stress is 700. A, the mean floor size for A is 1.5 cm, and we need to convert it into m, which is 0.015 meter, and we get that is equal to 200.5, and it just exceeds the critical value, the fracture toughness for A. Therefore, A cannot be chosen. However, for C and D, their fracture toughness is still didn't exist by their stress intensity factor, and therefore C and D can be chosen. And because the cost of C is more than the cost of D, C is the best choice. For things can be chosen, it must satisfy the safety requirement first. But when we consider the best choice, we can consider their cost. That's the logic behind the answer of this question.